So we're looking for maximum and minimum values in multivariable functions. Let's just go back to single variable calculus for a second. And when we were looking for these minimum points, we found this was a place where the slope was flat, so the derivative was equal to 0, and it was a maximum, so it was concave up, so the second derivative was positive. And those two bits of information said that that was a minimum. If it was upside down, that was a maximum. The slope was still flat, so the slope was 0, and the second derivative is negative. So that one said maximum. So there's our, from single variable calculus. So we need to take this and sort of extrapolate this to higher dimensions. So let's take a look here. There's a multivariable function, and just from looking at it, I can see two minimum. It doesn't look like it has a maximum that goes all the way up to infinity like that, but there seems to be two minimum here in the bottom, and this is also, I would say, a critical point. There's some place in the middle here. Now, okay, a critical point. Let's go back to what we were talking about in single variable calculus. We called this minimum a critical point. We called this maximum a critical point. We also called things like this critical points, the place where the slope was 0, but it wasn't a maximum or wasn't a minimum. But these were all critical points, points that we should pay attention to. They had potential to be maximum or minimum. So in 3D, this clearly a minimum, local minimum. Again, we're going to pull out the same language as we had in single variable calculus. We're going to talk about global maximum and global minimum and local maximum and local minimum. This point in the middle here seems like a critical point. It's important, but it's not a maximum or a minimum. It's not a local maximum or a local minimum. Now, let's just sort of find those three critical points. What's special about these three critical points? Well, their slopes in the x direction and their slopes in the y direction are 0. So whatever function, it's the function x to the fourth plus y to the fourth minus xy all times 4. That's what I've graphed here. But whatever function we're looking at here, the derivative in the x direction is 0, so it's flat, and the derivative in the y direction is 0, so it's flat, and that's true for all three of these critical points. That's going to be how we find the critical points. We take the two partial derivatives of our function and set them equal to 0. So the curve is flat in the x direction and flat in the y direction. If it was a minimum, it would be flat in both directions. If it was a maximum, it would also be flat in both directions. And if it was one of those middle points where if I looked at it, it was in one direction, it was flat but concave up, and in the other direction, flat but concave down, that would still be a critical point. So solving for all of the first order partials being equal to 0 is how I find the critical points, the potential maximum or minimum values. Now, if I have a function of two variables, I'm going to have two partial derivatives, and that'll give me, and set them both equal to 0, that'll be two equations, two unknowns. I can solve for the x, y points. Now, when we find them, then we have to classify them. It's a typical midterm final exam style question. Starts off with the phrase, find and classify the critical points of the function. So step 1 is the finding. That's setting the partial derivatives equal to 0 and solving. Then the classifying is deciding whether they are maximum or minimum or saddles. A saddle looks like this middle point in here. That's a saddle point. It's neither a maximum nor a minimum. If I look at it like this, it looks like kind of maximum E. If I look at it like this, let's look from the inside, it's a minimum. So in one view it's a maximum, in the other view it's a minimum. It's a saddle point. So how do I classify them after we found them? Well, we're going to use sort of our equivalent of the second derivative test, our multidimensional equivalent for the second derivative test. We calculate this d value. Now it has to do with the second derivatives. That makes sense because in single variable calculus we were classifying critical points as maximum or minimum by seeing whether the second derivative, the concavity formula, was positive or negative. We were saying that was maximum, that was minimum. It makes sense that the second derivatives are involved, but when it comes to functions of two variables, we have three second derivatives, two homogeneous partials, the derivative with respect to x and then x again and then or y and then y, and one heterogeneous partial, xy. Take the derivative with respect to x first, then the derivative with respect to y. And I know you're thinking, what about, well, you're not thinking that actually, but someone might be thinking, what about y and then x? But then you would tell them, Clairaut's theorem says that they're the same thing. So read this d is like our second derivative test equivalent, our measurement here. You could think of it as homogeneous partial times homogeneous partial minus heterogeneous partial times heterogeneous partial. It's just that those heterogeneous partials are the same thing. And those of you with linear algebra experience might even be thinking of this as the determinant of a matrix. So I'm going to write that matrix in. This we don't need, but I just want to put some foreshadowing here. It's the determinant of this matrix made up of all four second derivatives. These off-diagonal elements are the same thing. I've written it at fxy and fyx so that it's row column. But if I take the determinant, that's what I'm getting here as a value. If we don't want to think about determinants, you can just think of this as an expression. All right, how does this help me? Well, if the d value is negative, then it's a saddle point. If the d value is positive, then it's not a saddle point, it's a maximum or a minimum. Now how would this make sense then with our, let's go back and look at our saddle point that we have a picture of. So if I look in the y direction, this looks like it's concave down. So the second derivative in the y direction, f sub yy, looks like it would be negative. If I look in the x direction, now it also looks like it's a negative value. So go back to the d part here. This would be a negative times a negative. This would be a positive value. I can see it's a saddle point though. So then this second derivative, the heterogeneous second derivative, must be more negative, the product here, than these two pieces put together. If our d value is positive, then it's either a max or a min. How can I tell if it's a max or a min? You just have to check one of the homogeneous f sub xx, if it's positive or negative. This part works just like it does in single variable calculus. And some people will say, can I check f sub yy and get the same result? Yes, you can. It's just traditionally we use f sub xx. But you could do the same thing, f sub yy being positive, f sub yy being negative makes it a min or a max respectively. So a question that's find and classify the critical points, find, set all the partials equal to 0, classify, use this d value here. Let's do an example. So now it's going to be, here's our multivariable function. We need to find, first it's, so example, what are we doing? Find and classify the critical points. I need our z sub x. So I'm differentiating, that's going to be 4x minus 0 plus y. So there's our first slope formula in the x direction equal to 0. I also need z sub y. Set that equal to 0. So that's going to be 0 minus 1 plus x is equal to 0. So here's two equations, two unknowns. We solve them. Well, the bottom, let's look at the bottom equation first. The bottom equation solves only if x is equal to 1. If x is equal to 1, then the only way to solve the top equation is y is equal to minus 4. So we only got one, well, these are two lines, right? The two equations are two lines and they intersected at one point. Our critical point then is 1 minus 4. The slope's flat in both directions there. So there's our critical point. Is it a maximum or a minimum? Well, we got to calculate this d value, so I need all the second derivatives then. So let's get our second derivative with respect to x. So that's going to be 4. I need our second derivative with respect to y, which is going to be 0. And I need the heterogeneous, so I could take this that's already been differentiated with respect to x and differentiate it with respect to y and get 1. Or I could take this that's already been differentiated with respect to y and differentiate it with respect to x and get 1. Clairaut's theorem promises me I'm going to get the same thing. So now I've got the d is equal to 4 times 0 minus 1 squared. So I just care that it's negative. If it's negative, it's a saddle point. Question's over. One critical point and it's a saddle point. Let's draw this, or let's see what this looks like. 2x squared minus y plus xy. Because we can just modify what we have here. Two x squared minus y plus xy. Oh, my window's too small because I only go to 1 to 1. So we have to go all the way out to, if I want to see this critical point of 1 minus 4, I got to make the window, like, how about all the way out to 5? All right, well, okay, I can see the saddle point. It's right here. Yeah, that's where it's both. Y is near my, y is supposed to be minus 4, x is 1. Yeah, that's the saddle point. It's concave up this way and concave down that way. To see it better, let's just make our y minimum more just for funsies here, so that it's clear that this is a saddle point. Slope is flat in both directions, but it's not a max or a min. Let's look at another example. So, same idea. I got to find the critical points. So, I need the derivative, I need the two derivatives. The derivative with respect to x, so that's going to be 8x plus 1. I need the derivative with respect to y, which is minus 4 y cubed. That's it. Two equations, two unknowns. Again, I get one critical point. The x critical point is minus an eighth, because I'm setting these two derivatives equal to 0, and the y is 0. So we'll classify that critical point. I need all those second derivatives then. All right. 8 z sub y minus 12 y squared and z sub xy. Again, something Clause's theorem, doesn't matter. It's 0. So then d is equal to this value times this value. So z sub xx times z sub yy minus 0. And we want this evaluated at the critical point. So I need to plug this in. And when I plug this critical point in, I get 0. If it's negative, it's a saddle. If it's positive, it's a max or a min. We don't have a conclusion for equals 0. Yeah, this totally happened to us. This totally happened to us in single variable calculus as well, right? When the second derivative was positive, we had an answer. When the second derivative was negative, we had an answer. When the second derivative was equal to 0, what did we do? Now I know you're thinking, inflection point, yeah, maybe, but we had to stop doing the second derivative test and we had to go to the first derivative test, which was like draw a slope line and figure it out. So we either have to, we know what the critical point is. We have to sketch this, or okay, we could draw this, but let's not. Let's just look at this for now. Let's think about taking slices. So what if I take the slice of this surface when y is equal to 0? In other words, it goes through the critical point. If I were to take that slice when y is equal to 0, my z function is, it's an upward facing parabola. So it has kind of a maximum flavor. No, it's going up. It has a minimum flavor there, right? Upward facing parabola. If I take the slice when x is equal to minus an eighth, so going through the critical point, but this time parallel to the other plane. When I do that, I get, well, let's see. That's going to make this 4 divided by 1/64. I'm just looking for the shape, so I don't have to really clean things up that much. Minus a sixth, or minus an eighth. And what kind of shape is this? Well, that's with this minus y to the fourth, that's bent downward. So in the slice with the y equals 0, it's upward, and the slice when x is equal to minus an eighth, it's downward. That's telling me it's a saddle point. So I'm actually thinking about the shape here. So I'm making my conclusions that it must be a saddle. We could draw this and see it's a saddle as well, but algebraically we can see that it must be a saddle. So this was inconclusive when we get that determinant piece equal to 0. All right, so we did an example where we got a clear saddle point. We got an example where that whole thing didn't help us out. Hopefully, the next example is something that max or min, so we can see that working. Same idea. I need my derivative with respect, I got to find the critical points. So finding the critical point is going to be 8x. I'm taking the derivative with respect to x, and I'm setting that equal to 0, and I'm taking the derivative with respect to y, and I'm going to let that equal to 0. So that's going to be 4y cubed. Two equations, two unknowns. Before I go any further, though, just let's clean these equations up a little bit, just so we can look at them. This is the equation y is equal to 8x cubed. And this is the equation x is equal to 4y cubed. Now, how do I solve this? Two equations, two unknowns. They're not linear, so I can't do anything fancy like elimination or anything. I think what I need to do is just, here's y equals, I'll just sub that into here, and then get an expression with x equals 4, this thing cubed, and then just solve for x. But before I do that, so I'm going to solve it with substitution, but before I do that, I want to see something by inspection. By inspection, I can see that that 0, 0 solves this, that 0, 0 is a critical point. So I'm just going to write that down. Zero, 0 is a critical point. It solves this equation. Are there any other critical points? Let's see. Now I'm setting the, I'm writing the x is equal to 4y cubed. And here's what I'm substituting in. Okay, so that's going to be x is equal to 8 times 8 cubed. Times x to the 9th. Okay, let's divide both of those equations by, let's cancel out an x on both sides. So that's going to be 1 is equal to, now you're looking at this going, why hasn't he gotten a number for this 8 cubed thing? Well, because maybe I don't have to. There I canceled off the x. Now solving for x, I'm getting x is equal to, that's going to be 1 over this expression. Well, that would be x to the 8th. So I'm going to take the 8th root of this whole thing. Oh, wait, got to be careful. Taking the 8th root's like taking the square root. There's going to be some plus or minus floating around too. Now, is there anything clever I can do here? Can I get kind of 8 points? Let's turn this into 2's. This is 2 squared. This is 2 cubed, so this is 2 to the 9th. And that makes this 2 to the 11th. So we can write this as plus or minus 1/2 to the power of 11/8. Looking for critical points. Now I've got the x value of critical points. I've got 2 x values of the critical points. So let's find them. If x is equal to the positive version of this, then y is equal to, I got to go all the way back up here, 4 times this thing cubed. So that would be 4. If I cube this, this would be 33. And if it's the negative, oh no, these are x's, so that's going to be an 8 on top of that. And if that put in the negative here, the negative comes out of the cube, so I'm going to get the negative of that. And if I want to get, fancy, 8 is 2 cubed, so I can cancel the 2 cubed off both sides if I should like to. Let's not. So I've got now 3 critical points. It's a good thing I found that 0, 0 first by inspection, because there's a good, I didn't point it out, we kind of missed it as we went through the algebra. Where did we miss it? We missed it right here. When I canceled an x off both sides, I'm like dividing both sides by x, which is totally valid algebraically unless x is equal to 0. So if I didn't make note of it ahead of time, when I got to this step, you would have to have gone either x is equal to 0, in which case y is equal to 0, or this is true. It's a lot easier to see it by inspection first, and then do the rest of it not worrying about the 0, 0 origin. So now I've got 3 critical points. We got to classify them. So I need, so I'm going to have to get all of the, I need the second derivatives. So I need z sub xx. That's going to be equal to 24x squared. I need z sub yy. That's going to be equal to 12y squared. And I need z sub xy. That's going to be equal to -1. So D is equal to, that's going to be weird here. D is equal to 24x squared times 12y squared minus this piece squared. Minus 1 squared is 1. So there's the D part. Now I need to use it to classify all 3 of my critical points. So I'm going to write it like this. D, and I'm going to go subscript at the origin. I'm going to plug in x equals 0 and y equals 0, and I get, if I make x equal to 0 and y equal to 0, I get minus 1, so it's less than 0. So then that means the origin is a saddle point. Done. Next, we're going to plug in the other points. But note to self here as I put them in. Take this. Let's put the first one in there. That's going to be 24 something squared. It doesn't matter whether I put the plus and the plus in here or the minus and the minus in here, because they end up being squared. So the value of big D will be the same. So I'm just going to end up, I'm going to plug them both in at the same time. That's equal to all right, the x value is this, and when I square it, it's going to be positive, and the y value is this. All right, this looks like it's got a lot of stuff in it, but I just care if it's positive or negative. So I only need to evaluate this down to, a level if I can decide is this highlighted part bigger or smaller than 1. Let's just go simplify. Wow, that's pretty cool. Who knew? It simplifies down to be 8, which, more importantly, is positive. That means that these critical points are either maximum or minimum. So I need to look at, so that means max or min, so I got to check the second derivative now, evaluated at these points. But the second derivative is positive, concave up. So those are minimum. So now those are both minimum, and 0 is a saddle. So let's finish our question by finishing the answer. That's a saddle. And those are minimum, local minimums. What does this look like? Well, this is going to look like the first graph that I drew with the two, looks like, to me it looked like a pair of pants. Two x to the fourth, y to the fourth, minus xy. When I draw it like that, it's hard to see, right? The algebra is telling me that I'm getting these two little kind of tips down like that are the minimum. We could zoom in to look at that a little bit closer. Oh, the x is too big here. Okay, it's subtle, but there they are. Those are the two minimums, and there's the saddle point at the origin.